One and all. I, Shweta Surishma, welcome you all to the day 4 of IEEE sponsored FDP on recent tools for integration of smart systems. Today we have Dr. Arpit Ravankar with us as our eminent speaker. Sir is HOD of Electronics and Telecommunication Engineering at Vidyalankar Institute of Technology, Mumbai. To brief about his education, Sir has completed his postdoctorate from Tata Institute of Fundamental Research, Mumbai, PhD from the Graduate University for Advanced Studies, High Energy Accelerator Research Organization, Japan, Masters of Technology from Widget AI, Mumbai. Sir has total of 12 years of experience with 70 plus publications in journals and conferences. I would like to welcome Sir and hand over the session to Dr. Arpit Ravankar. He'll be delivering a talk on simulation using LabVIEW software. Welcome, Sir.
Thank you, ma'am. Am I audible, ma'am?
Yes, sir, perfectly.
Okay. So, thank you for inviting me for this particular session. So, today I'm going to deliver a hands-on experience session for the LabVIEW. And in that case, I will go with some real lifetime problems that we can actually simulate and we can do. So, with your permission, ma'am, I want to start the session now.
Yes, please.
So, good morning, all the participants. So today we will see what we can do with the LabVIEW. The LabVIEW is a particular software. It's developed by National Instruments. National Instruments is a US-based multinational company. Its main domain is basically instrumentation and provides electronics and softwares related to instrumentation model. This is the first, you can say, a multinational company which has actually provided a graphical user interface, and it's a very widely popular tool, simulation tool, as well as the hardware interfacing tool that's available today. If you visit any industry, any automation, any manufacturing industry, you will find this particular software is being used for overall monitoring of all the parameters of industry, as well as you can interface all sorts of your devices. So basically it provides a graphical user interface. That's what I will like to start with. So see, I hope all of you have a LabVIEW installed in your PC. I'm using a LabVIEW 2020 version, but doesn't matter, like even if you have a LabVIEW 12, LabVIEW 7, that's also same. So all programs in the LabVIEW is called as a VI. Okay, what is a VI? VI is a virtual instrumentation. So if you see that here the LabVIEW, the word LabVIEW stands for a laboratory, VI stands for a virtual instrumentation, and EW stands for an engineering workbench. So overall, the full form of this software is a laboratory for virtual instrumentation engineering workbench. In this particular software, we don't write a program, we draw a program. So that's why all programs are called as a G language. This is a graphical language, and you get a graphical user interface. Okay. So you clicked on a blank VI. Okay. How to get a blank VI? You can just you can go to the file, or you can just select a new VI. That's also a new virtual instrumentation. So whenever you select on a blank VI or a new VI, so what you need to do, you go to file and select a new VI. Okay, so these two windows will pop up. Okay, so you can see that one particular window is this gray screen, and this another particular window is a white screen. Okay, this is a gray screen, and then this is a white screen. This gray screen is called it as your front panel. Okay, and this white screen is called it as your block diagram. So you see that virtual instrumentation means designing an instrument. Okay, that instrument can be a mechanical in concept. That instrument can be an electronics. Instrument can be related to any industry or any educational purpose. Okay, so see that this particular instrument, that's whenever you see a particular instrument, so that instrument, suppose you can imagine a particular oscilloscope. Okay, so we all have used an oscilloscope, or DSO, digital storage oscilloscope, or network analyzers. So what is the feature of that particular oscilloscope? You see that there is a some screen, okay, where we actually see some waveform. There are certain knobs, some switches are there, okay. So basically this instrument oscilloscope consists of some controls and indicator. What's an indicator over there? An indicator is basically the display where you see that particular waveform graph, waveform chart, okay. And then there are some switches from which we control that waveform. We change the time span, we change the amplitude, okay. So that things are called it as a controls, okay. So with these switches and knobs we actually control, and with that screen we see as an indicate, we see some graph, that's an indicator. So any instrument is consists of some controls and indicators, okay. And then when you try to open any instrument, what happens, these controls and indicators are connected with some processor, and some mathematical logic is present in that particular processor. that that processor is driven by a certain mathematical logic. So you see that when we want to design a particular instrument, we need to create a controls and indicators on a front panel. And how to connect these controls indicators, what is the purpose of those controls and indicators, how they process a particular signal, that will be done in a block diagram. So see, the key is a control E. When you press a control E, E for elephant, you can switch from this gray screen to white screen, okay. So you see that I press a control E, so from gray screen to white screen I can switch, and again I press a control E, I can switch from white screen to gray screen. If you want to see both the screens, okay, front panel as well as block diagram, you press a control T. If I press a control T, half screen of my desktop will be a gray screen, and half screen of my desktop is actually a white screen. So now just I press a control T, and now see, this is gray screen, this is a front panel. This is how my instrument looks from outside, okay. How many controls are there, how many indicators are there, and this white screen is basically how these controls and indicators are actually connected with some mathematical logic. Okay, so I don't waste much time and I will start this particular session. So see that here, when you right click on this gray screen, you will get all sorts of controls and indicators. So see that if I right click on the gray screen, this front panel, so then I can see the numeric controls, numeric indicators, okay. There is some meter, there is some dial, knob, tank, thermometer, okay. So this list is endless, so many. And you see there's you go to graph, you can see the chart, waveform graph, intensity graph, so many indicators are there. A boolean also, so you can see the LEDs are there, some switches are there. So we can create any controls or indicators on the front panel, and its reflection will be exactly on the block diagram. So suppose, take an example, I right click on my this front panel, okay. So and I go to boolean. If I right click on my front panel, I go to boolean, I can see the digital logic controls and indicators. What's a digital controller? There are some switches. And what's a digital indicator? There are some LEDs. Okay, so suppose I drag and drop this particular LED. Let's say this round LED I want to select. So what I did here, right click, go to boolean, and select some round LED. Okay, so this green color LED, you just click it, left click, and this LED will be appearing on your front panel. And see here, you can see there is a boolean. I will just zoom it. I'm zooming it because you all are able to see, should be able to see it. Otherwise, no need to as such zoom it. And you see that I can actually increase the size. If I move my cursor towards this particular LED, I can actually increase the size of this LED. Okay, here also I can do the same. Okay, so see that I have created a one LED on the front panel, and its reflection is exactly on the block diagram. So see that a complete replica is here in the block diagram. Now this LED, if I click it here, it turns green, it turns dull, bright, okay, like that. So this LED is exactly reflected over here. Now suppose, now you see that how to control this particular LED. Okay, so now see here, here there is a one LED, and here there is a one digital indicator. So if I want to control this particular thing, I need a particular switch. Okay, if I want to control some LED, I need some switch. Basically, there are only two states of an LED, that's on and off. Suppose I select a one switch. So I have to again right click on the front panel, go to Boolean and select a switch. Suppose I select this push button. Okay, so what I did, right click, go to Boolean, select this push button. I selected this push button. Somewhere here I can put it. Okay, I can zoom it. Okay, and I can increase its size by moving my cursor. Okay, so now basically there is a LED and switch on the front panel, and you can see the both things on my block diagram also in this white screen. So now let's name it as a switch in. Okay, let's name it as an LED, so it becomes much more easier to understand. Okay, so there is a switch and there is an LED on my front panel. Now automatically its reflection is in the block diagram also. There is a switch and LED. Now what I need to do, I need to just connect the wires. You see that I take a wire, I move my cursor to this block diagram, this white screen, and this cursor changes to a wire mode. You can see it changes to wire mode, and just I left click and move my wire like this, and I stop here. So you see that a switch and LED are connected by a green wire. Now here LabVIEW deals with the different types of data. Okay, some data types are there. That's analog data type, there is a digital data type, there's a string data type, there's a VForm data type, there's an integer data type. So many VForms are there. This wire thickness also depends on whether it's one-dimensional data or it's a two-dimensional array. So thickness of wire also changes. You see that this LED is green color indicator here in the block diagram, and this switch is also green. And here you see that there's a green wire connecting both switch and LED. Okay, so switch and LED are being connected with this particular wire. That's also green. So it shows that a digital control. What is a digital control here? There is a switch. What's a digital indicator here? That's an LED, and both are green, and wire connecting them to is also a green. Now I run this program. You see that in the front panel and in the block diagram there is this arrow button. Okay, so let's zoom it. Okay, you can see just below the file and edit there is some arrow button. That's a run button. Okay, so you press that run button. Okay, now switch is off, so LED is off. Now I turn on this switch. Okay, just click on this switch and again press this arrow button. Just below the edit, file, edit, view, just below the edit you will find this run button. You press this, now this LED is turning on. Just beside this run button, there is a run continuous. If you run continuous, now see, if I change the position of this switch from on to off, this LED is off, it is on. Okay, so like this we can actually make a digital logic implemented in the LabVIEW. Now see that basically this switch and LED, they are not physically present. Okay, they are virtually present. I have virtually created a switch and I have virtually created an LED in my laptop, and they are not physically present, they are virtually created. So that's why this particular instrument is called as a virtual instrumentation. So all programs in the LabVIEW are called as a virtual instrumentation. Okay, so this is a one very simple type of basic understanding that how to use this particular thing. And if you want to stop a particular program, you see there's a run button, okay, arrow button, then there is a continuous run continuous, and just beside that there's abort execution, this red color switch is there. You press this program automatically its program automatically is turned off. Okay, this was a one type of data. Now let's see the different types of data. So see, different types of data are analog. I right click here, go to numeric, and in this numeric, okay, I will see all my analog sorts of data. Okay, so these analog sorts of data are like a thermometer, tank, some meters are there, some waveform charts and other stuffs are there. So see that suppose I take this thermometer, or let's see this meter is there. I select this meter and drag and drop somewhere here. So this meter is over here. Okay, so there is a meter. Now this meter is basically, you see the values from 0 to 10. This doesn't this is not included in a boolean logic. So this is basically an analog concept. So meter is included in the analog data type. This is basically an indicator. So meter is an analog indicator. Now press a control E, you will see that there is an orange color a meter is being reflected over here. Okay, so there's a meter, and you see now I can't connect this to switch on already because the meter requires something that is an analog. Okay, so what I can do here, I press control E here, I provided this I provided some with the analog controller. I right click here, go to numeric. Okay, in this numeric part I can actually select anything related to, let's say, uh, I can see select this vertical pointer slide. You can select any sort of controller. Okay, so there is a slider and there is a meter. I can actually slide it like this. Okay, and accordingly the values should be changed in the meter. But I have to I have to connect this to press control E, and you see there is a meter and there is a slider over here. So you see now these two is completely orange type icons. You see the slider is also having an orange box and meter is also is in orange box. So these two are analog data type. If you wire them by moving the cursor, the wire is also orange. This exactly shows that different data types require different types of wiring, and that wiring is actually done with a different coloring. Now this slider and meter, this part is also done. I press Control E and I run the program. Just below the edit, file edit, just below you will find a run button, arrow button. Run it, and now change the, just beside that there is a run continuous, and in this run continuous you see that as I change the value of slider, the values in the meter is also being changed. Okay, as I change the position of a switch from off to on, the LED is turned on. So both thing we can do simultaneously. There is some digital logic and some analog concept being implemented at the same time. Okay, so this is a one basic example I wanted to, because some of you might not be aware about the LabVIEW. So just wanted to have a brief overview of this particular software. There are so many tools, so many graphs, charts, and so many different stuff that we can actually do with the LabVIEW. Okay, so because I get to know that most of the participants here are from different backgrounds. Some are from electronics, telecommunication background. Some are from mechanical background. So I thought I should do some examples or give us some hands-on practice on measurement of a vibration. Okay, so basically I selected a topic related to the sound files. Okay, so acoustic files. So acoustic files are basically acoustic signal we use in electronic communications, also in mechanicals, in chemical engineering. Most of the engineering branches make use of this particular acoustic signal. So I thought better to implement a particular program so that all of you can be familiar with that acoustic signal. Okay, so I turn off this program by selecting this red terminal, this abort execution. Okay, I want to start a new program. So before that, I need all of you to have a certain files. That's like I can put it in the chat box. Just wait. Just a simple few KB files are there. Okay, there are some files are there like this M99 file. This is basically a biosignal is there. And let's have one more file. It's a heater, house heater. Okay, so I have sent two files. Okay, two sound files. That is, one is related to heartbeat. Okay, and second is related to a heater sound. Okay, there is a room heater is there, so it makes certain sound. And what we can do when we actually analyze this particular sound with this particular software. So I hope all you have access to these particular files. That's I just put it in this chat box. Okay, so I start with the my program. Okay, so I now select go for the file and select a new VI. Let's minimize this program. Okay, so now I have a screen, front panel and a block diagram. Okay, front panel and block diagram, these both are with me. Now I need to play with certain sound files. Okay, so before that you need to understand the concept of reading a particular file. Okay, so suppose you have a data like you can have a data in a Word file, you can have a data in an Excel file, you can have an image, you can have some sound file, acoustic files. Okay, so there are different formats of a particular file. Okay, so see that there are different formats of a particular file. So now here in this case, I want to go with the this particular sound format. So before that, I just right click here on the front panel. So all of you right click on the front panel, go to string and path. Once you go to string and path, so देखो यहाँ पे first row, third column, you will find a string and path in the front panel, and you will see there is a file path control. Okay, so just select this file path control like this. So there is a file dialog box is there. I can increase its size. Okay, so here I can actually give a path where my file is located. So here, suppose I select on this file dialog, and it will lead to my files where actually I have stored my files. So it will ask where my file is located. I can go to this particular folder where exactly some files are located. So let's select this house heater file that I have given to you. So I selected this house heater file. You can see that in the C drive in this particular folder BD, there is a house heater 1.wave. Remember that if you want to analyze or process any sound file, the sound file format is .wave. So here you can see that there is a .wave file. Okay, this .wave file should be there. Suppose you have a file in an MP3 format. So there are ready-made apps are available where actually you can convert a MP3 file to a .wave file. So .wave file is actually a basic standard that is being used for the LabVIEW. All sound files need to be converted to .wave. If you just Google that you want to download some sound files for the LabVIEW, it will direct you so many sites where you can have various sounds related to nature, related to machineries, related to biomedical signals, and all files will be in the format of a .wave. So it gives you an option to actually select a .mp3 file or .wave file. Okay, so this is a particular file where actually I have got this particular heater one, house heater one .wave file. Now these file will be read by the LabVIEW if I use the file IO concept. Okay, file input and file output concept. Let's go to the block diagram, press Ctrl E. Now here there is a block diagram and there is a path because I have created only one path in the front panel. Now this is not an indicator, okay, this is a control. Okay, here I can change this particular path. So this is a control. Now see in the block diagram, Let's zoom it. This is a path file. You can see the color is green, so it's basically represents a digital logic. Okay, so this path file, now I have given a certain acoustic file or a sound file. I need to read it. Okay, so I right click here. Okay, I right click here, and all of you, you can go to the 1, 2, 3, 4, 5, fifth row and second column and the graphics and sound. Okay, right click on your block diagram, right click on this particular white screen, and here you will see a graphics and a sound library. In a graphics and a sound library, I can again show you. Right click in the fifth row. There's a fifth row, second column. There is a graphics and sound. In this graphics and sound, go to sound. Last row you can find the sound. Okay. Now in the sound, you have to go to files. So see, the path is big, but once you are familiar how to find a particular function, you can then practice it, and then you don't need to remember it. So right click, go to graphics and sound, and then go to the sound, and in the sound, go to the files. Okay, and in the files, there is a simple read file. Okay, so in this simple read file, you see that there is a simple read and simple write. Whenever there is a read, there is a specs. Okay, a reading specs are there, and whenever there is a write, there is some pen is there. Okay, this is a basic way to identify which is read and which is write. Of course, it's written over here, but you need to understand there's a specs here and there's a pen here. So just simple read. You drag and drop somewhere here. You can label it so that it's visible, and I can zoom it. Okay, so now my program is that I have given a certain path for an acoustic file, and now I have created a sound read file. Okay, now this sound read file, what does it do? If I want to see it, then the best way is using its library information that's given in this question mark. Okay, where is the question mark? If you see your block diagram, the top right, you can find a question mark over here. Here is given a show context help window. On the right side, top right side of your program, you can see a question mark in a block diagram or in the front panel, but here we are in a block diagram. So just click on that yellow color question mark and move your cursor to sound file read. Automatically here you can see that it gives you everything, every information about the sound file read. Okay, so what I just did, I move my cursor to this particular question mark, and I click that question mark, and I move my cursor to sound file read. Now you see that there is a green color path. Okay, a green line is there for a path connection, and there's a brown wire connection for a data. I am interested only in these two aspects because sampling and other stuff, you can do it as per your requirement. Okay, how many samples you want to implement, how much a sampling rate, all those information you can do here as per your requirement. But here we are trying to acquire a particular sound signal. We want to see a particular sound signal. So here there is a path, there is a sound file, and there is a data. Okay, so see, there is a green color wire at the top. There is a path. Now I move my cursor to that path point in this. Automatically a path is being reflected here, and I connected path to my path. Okay, just like that. So this is a path is being given to this sound file read. Okay, so which file to read? Go to that path and see what sort of file is over there. Okay, so first this sound file read, we checked that what path of that acoustic file is given to it. Okay, now on the right side you see that there is a brown color wire that is called it as a data. Of course, there's a path out, data, offset, error, so many stuffs are there. So this data is there. Now this data you need to plot. Okay, so I want to plot it on some graph. Okay, so press Control E. In this front panel, you will switch to a front panel. In this front panel, now go to right click on your front panel, and second row you will find a graph. Okay, in the second row you will find a graph, and here you can select a waveform chart. Okay, so some indicator or some chart is there. So what I'm doing, right click, second row, there's a graph, and here there is a the graph, select a waveform chart. Don't select a waveform graph, select a waveform chart. Now this is a waveform chart I have selected over. I will increase its dimension. Okay. So there is a particular file over here. This is a waveform chart. Okay, so on the front panel I have these two stuffs, file path control and a waveform chart. And press Ctrl E, you see that our waveform chart is an orange color indicator because it's an analog. So I can connect it to a data. Now what you need to do, this orange color indicator, you need to connect a data of sound file read output. Now see, this is a very basic concept. Sound file read requires an input. Where is your sound file located? So we have given a path where exactly in my PC or in my desktop, laptop, where my file is located. That's a path. Now whatever data is there that I have connected to a waveform chart, you see that path is connected with the green wire because it's a digital logic. The data is connected with an orange wire that because it's an analog concept. So there are certain types of library where where the input is a digital but output is analog. Okay, now see that this is a program. Now press a Control E, and I plot it. I run this program. So just run this program. Now see, whatever that heater wave is there is being plotted, but actually I haven't heard any voice here. Why? Because I haven't put an output sound file here. Okay, so there was heater noise was there in a room. A room heater was on, and this was the heater noise. You see that it starts with the 530 54 and it starts with the 59, some 5 second or 6 second this sound file is there, but I can see there is a certain plot. Now I want to play it. How to play it? I press a Control E, go to this particular block diagram. I right click here. Okay, just again I have to go to graphics and sound. Okay, initially we found this sound file read in the graphics and sound. There itself we will go. We go to graphics and sound. Again we go to sound. In the sound we go to output, and in the output we go to play waveform. So I'm telling you again, right click on your block diagram, go to graphics and sound. In this graphics and sound, go to sound. In this sound, go to output, and now play waveform. Just select it, drag and drop somewhere over here. Okay, so now a window will pop up. Okay, there's a window. This will show that you want to play a waveform, you want to play a sound, you want to play some acoustic file. You need to check your speaker setting. Okay, so I click here test device. So there is a blip. You will hear a blip if you test device, so that your speaker is working fine. Okay, when you try it, automatically it will lead to, see there's a channel 2. Automatically your head, now I'm using a headphone, so it is a its ID is 0. If you are using your desktop or a laptop speaker, its ID is automatically 0 over here. So headphones, Realtek R audio, its address is 0, sample rates, sampling frequency, and channel is given, and you can test this device. So if a blip is you hear a particular beep, so that means your speaker are working fine. I press OK. Okay, now I connect this data. You can see there's some data. Okay, data line is there and it's the input side. I connect this data wire to this brown wire. Okay, so this program now makes some sense that I am reading a particular file. I want to read a particular sound file whose path is given on the left side. That sound file will be played with this play waveform. So I will hear certain sound and at the same time I will be able to plot it on a waveform chart. Okay, so now I press a control E. First I will clear this chart because it's already being plotted. How to clear a particular chart? Press a control E, go to the front panel, right click on your waveform chart, go to data operations. So data operation you can find somewhere 1 2 3 4 5 6 8. On the 8th row, you will find the data operation. In the data operation, just clear this particular chart. That's done. Okay, so there is a waveform chart, and there is now this waveform chart is clear. So whatever data was already present in the waveform chart, that's being clear. Okay, now I again run this particular file. Now what will happen? The file will be plotted first because plotting already the LabVIEW software has already acquired a certain data. Okay, it's very fast. Data acquiring is very fast, but sound is several seconds long, so it will keep on playing. So you can hear the that particular sound of that heater sound, the room heater noise, and automatically it gets played. I will change the color of this waveform. So let's keep it green. Can increase the thickness also. Okay, let's play this. So I run. So now you are hearing certain sound. So now see that what I did particular file, I use a file path, I plotted a waveform chart, and at the same time the file was played. Okay, so this is we can analyze a particular file. Now I got an amplitude versus time response for this particular file. Now so you see that y-axis is an amplitude and x-axis is actually the time. So whatever sound file was there, I got an amplitude and time response with this particular thing. So this information now I can use it for my further signal processing. Now as a mechanical engineer, if you want to go for some vibration related studies, because what happens when you design a particular instruments, you need to go for the it's a vibration analysis, because the vibration actually generates a certain sound. Most of the air conditioners and room heaters, they are excellent in their operation, but still they are very less in demand because of the noise they generate. Okay, so as an engineer, we need to work on this particular aspect. Any instruments like a electronic instrument, a heart, a biomedical instrument also should be completely noise free. So study a particular noise is a very important part of engineering, noise as well as the signal also. So this is a one complete amplitude versus time response. Now I just uh, make this waveform little smaller so I can improve my front panel again. Now I press a control E, and here I can now do certain analysis. Okay, so for that I want to see the power spectral density for this particular noise signal. So you see that this is a particular signal. This signal is the room heater noise, room heater sound. Okay, I want to see its power spectrum. Okay, at what time, what amplitude is there, how much of power of that particular thing is there. So for that I go to the block diagram, I press Ctrl E, I right click, and I go to signal processing. Okay, so now I'm using some library function, that is signal processing. You see that there is a structures, there is a waveform, there is a timing, there is a graphic sound, and here there is a mathematics, and here there is a signal processing. So just bottom from bottom there is a fifth or sixth row. You can find the signal processing. In the signal processing, there is a waveform generation, waveform condition, waveform measure. So many sorts are there. So go to the waveform measure. Okay. So see that, go to the signal processing, go to waveform measure. First row, third column is a waveform measure, WFM measure. Okay, so I will again show, right click, go to signal processing. In this signal processing, first row, third column is a waveform measure. Go to that waveform measure, and here you can see that fourth row is a FFT and power spectrum. Okay, so what is an FFT? Fast Fourier transform. If you want to see a particular time signal in a frequency domain, you have to use an FFT. FFT is a Fourier transform, a fast Fourier transform, a very fundamental engineering concept, mathematics concept is a FFT, fast Fourier transform. And from the FFT, actually, we can calculate the power spectrum as well as the power spectrum density, PSD. I select this FFT power spectrum at a row 4. I put it somewhere here. Let's reduce this program's space. You can label this particular thing. Okay, so now I have selected an FFT and power spectrum PSD. Now you need to see what are its properties. Okay, what inputs we can give it, what outputs we can obtain it. So I go to this question mark and select this FFT. Now in this FFT, now see that there is a time signal over here on the left. Okay, that's what I am interested in. There is a window also. So electronics engineers, electronics communication engineering know different types of Hamming window, Hanning window. So many windows are there that we can see here. There's a output, you see there is a pink color wire, there's a power spectrum and PSD. And at the top you can see there is a expert mode. So expert mode means you want to measure a power spectrum or you want to measure a power spectrum density. That's which mode you want to operate. So there are two particular things. One is this, on the left there is a time signal that I will connect with my waveform chart. The topmost signal, you see there is an expert mode, power spectrum or power spectral density. There is a, and right is a pink color where there is a power spectrum. So what I do, the leftmost part, time signal, I connected over here. Time signal means amplitude versus time signal. I want to connect it, I want to change it to amplitude versus frequency response. Okay, time signal should be changed to a frequency. This is an connected to an FFT. Now right side there is a pink color wire, power spectrum and power spectrum density. You move your cursor over there. Now every time you don't need to put a graph or chart on your front panel. Now this pink color terminal, move your cursor and right click. Once you right click, it will lead to a create. Okay, not needed. Okay, what we will do, we can create a graph indicator on the front panel itself. I press a control E, and here I will create a one more graph. I right click, go to the graph, selected a waveform graph. Now select a waveform graph. Okay, select a waveform graph. A difference between chart and graph is that chart gives you a continuous amplitude versus time. A graph is certain when a signal is complete for a particular, when signal has completed its execution, then a graph represents all of its values. So graph is like after completion of all the iterations, you get a value on the graph. Chart is a continuous, just like an ECG, electrocardiogram, you get a complete chart. Now this is a waveform graph. Okay, I name it a power spectral density, PSD. change the color as per my requirement. Okay, I have selected a graph. I have named it as a PSD, that's a power spectral density. Now here there is a power spectral density. Okay, now it's visible. Now connect this power spectral density to the output. That is a power spectral density output. It's connected. You see now its icon is converted from orange to pink. That means it is compatible with that particular data type. Okay. So power spectral density is connected. Now see this particular logic. What I am trying to do. I have just selected a sound file read. I have given it a path. I then connect it to a waveform chart where I can see amplitude versus time. I have connected to same wire. I have connected to a waveform data, a play waveform, where I can actually listen to that particular sound. Then the same wire is connected to an FFT power spectrum, and the output is given to a waveform graph. So in the front panel, if you see, there is a file path, there is a waveform chart, and there is a power spectral density. Now again, I play this waveform just to clear it. How to clear it? Right click, go to data operations and clear chart. Now I try to play this sound and see its power spectral density. Power spectral density will be automatically calculated as my signal is being plotted. The sound file will keep playing. So I run this program again. Okay. I stop this. Now see that here, suppose I reduce this. This is, I can change the amplitude, the time axis. You see, this is its power spectral density. Now this time axis is actually the frequency here. Now you see that here there is some amplitude versus time response was there, but here it is amplitude versus a frequency response is there, and I can see that most of my frequency components are dominant in 150 hertz. Okay, clearly you can see a certain peak. So it is as good as a very good a mini project sort of thing. You can actually select a particular sound file, you can see its amplitude versus time response, and based on that you can calculate its FFT and you can calculate its power spectral density. So this is a PSD, and most of the my frequency component, because the sound is having a certain frequency. Okay, it can go in a certain range, but the frequency is fixed and it is around 150 hertz something. So here this is a very good example that how we can actually see a particular file and actually acquire its certain characteristics. This was the one example that I wanted you to analyze a particular vibrations, analyze a particular sound, and then play with its component. Okay, now the second thing, most of the engineers are interested in using a histogram. Okay, histogram is not only used for your images. Okay, histogram basically gives you the pixel contents information in a certain with a certain samples. Okay, for certain image. But so for sound files also can have an histogram. We can have a histogram that we can see that where exactly our signal is lying. Most of the frequency component are present in a which particular part. That also we can see. So here I will like to see a histogram part also. So I right click here and I go to mathematics. Now just above the signal processing, there is a mathematics. Go to your block diagram. You go to block diagram, then go to your mathematics. In this mathematics, I think mathematics in probability and statistics. Okay. Go to mathematics. In mathematics, then third row, probability and statistics. Third row, first column, you will find the probability and statistics, and last row, last column is a histogram. You can select an histogram. Okay, so I select this particular histogram. Okay, like this. Let's place it somewhere here. So now the histogram shows that a sample data and sample results as a column chart. We get an histogram. Okay, whatever amplitude versus time response is there, its column chart representation, a bar chart representation is its histogram. Okay, I press an OK. I can again show that. Right click, go to mathematics. In the mathematics, go to third row. Third row, there is a probability and statistics, and last one is an histogram. Just select it, and again give the same signal. I connect the same orange wire to here, and histogram output is given here. On the right side arrow is there, a histogram output is there. Here I can right click, I can go to create. Now on the histogram output, move your cursor to histogram output. Here, when there is a right side arrow, right click here, go to create. In this create a graph indicator, or you can create a graph in the front panel. That's what I'm trying to say. Some modules are ready-made available in which you just right click, create a graph indicator, or you can create a graph indicator on the front panel and connect it. Okay, so I created a graph indicator and I can increase its size. Okay, so this is another part of our programming. So we have one particular sound file. We actually locate this file in our PC. We plot it amplitude versus time response. We play this particular file as a sound file. Then we calculate its power spectral density, and then we calculate its histogram. So somewhere here a histogram is generated. See, there is some space problem. No problem. I can just put my histogram over here. Okay. So now you see my front panel is completely filled up now. There is a file path control. There is a amplitude versus time response. There is a power spectral response, and there is a histogram. Okay, so that's, I can change the color. Now let's clear this power spectral density. Right click, go to data operation. Even if you don't clear, doesn't matter. Clear this graph, clear this chart, and run this program again. Yeah, now I stop this. Now you see that here, if I can see a certain two signals as a power spectral density signal. I can see the amplitude versus time, and I can see the histogram also. You see, this is my histogram. Okay, so I can see that with respect to as a standard deviation from the mean, where my signal is actually present. Now this is my particular histogram associated with that particular sound file. So as an engineer, it becomes very interesting when we study a particular vibrations related to any machineries, when we study a particular mechanical signals also, and when we study the biomedical signals, acoustic information tracing can be easily done with this particular thing. See, this is nothing is here simulated. I am taking a real time data. The sound file is being captured from a real setup, and then I am playing it over here. So one file I have given to you. Okay, so this is all those responses we can actually see, and this x versus y data we can further plot it to an excel by writing to an excel file. That's another part of reading from a file and writing to a particular file. We can give a path location, and we can obtain all this data on the excel also, or here in any indicators as an array indicators, we can obtain all these sorts of data. So this is a complete analysis of all these sound files. Now I have given a one more file. That file is basically this particular file was related to a mechanical engineering because it deals with the heater sound. Okay, now the second sound file that I have given on the chat box is basically a biomedical signal. That biomedical signal is from a unborn baby. Okay, so it's basically a heartbeat of a fetus. Okay, heartbeat of a fetus, and obtained with an ultrasound. So when an ultrasound is used on a fetus, then automatically that sound is being generated, and that sound is that the baby's unborn baby's heartbeat. What happens is there's a lot of fluid, and in that fluid, the baby heartbeats are very high. Normally, it goes to 140, 150 in that zone, and its heartbeats are very fast. So that I will like to plot. Now see, I change my file now. I go to the file path. Now here I go to the file path, and I have given this M99. Okay, that file I have selected. This is the M99 file. Okay, now this file will be plotted. This is basically a fetus heartbeat, unborn baby. Using the ultrasound, this particular file was obtained, and I play this particular information. So I get an amplitude versus time. So I basically what I see will be a heartbeat spectrum. The amplitude versus frequency response is a power spectral density and a histogram. So let's run this file. Okay, so many heartbeats I can actually see, very fast heartbeats are there. Okay, now I stop this program. See, the heartbeats are being plotted. So basically, this is not an ECG here. This thing is not an ECG. This is PCG. This is a phonocardiogram. Okay, there are different ways to represent a heart signal. The electrical activity of heart is called as the electrocardiogram. Then acoustic activity of the heart is basically phonocardiogram. This is a PCG, or many time it is called as a acoustic cardiogram, acoustocardiogram also being called for this particular signal. So you see that this is just the heart is a lub dub, that sound, lub dub, that particular sound. So this is a lub dub heartbeats for an unborn baby of a fetus obtained with an ultrasound. And you see the frequency response here, power spectral density. You see this is a power spectral density, the yellow color power spectral density. You can see that most of the frequencies is in this particular from 0 to 100. So frequency is less means so many heartbeats. Okay, let's see whether under 10 what I'm getting. See, so many frequencies from 0 to 10 here. Okay, if I analyze this a particular hearts, because this a complete time series is there. Okay, several 30-second signals are there, and so many time series are there, and I can see the frequency response here. Even in the first 10 seconds, so high frequencies responses are there. This is, and you see the histogram, a deviation from the mean, and where exactly my information is being considered. I can see the histogram also. This is a very important signal for biomedical engineers, for electronics engineers, and basically we can see the modulation of our signal with an acoustic wave. Telecommunication engineers many times use the acousto-optic modulator for detectors, for networking detectors. You see, the acoustic optic modulators, this means you have to modulate your signal with an acoustic wave. Okay, so most of the time the RF signal is being used. As in fiber optics, we use the Bragg gratings. In that fiber Bragg grating, the acoustic signal information is being used to modulate a particular crystal, and that crystal actually modulates the light wave, and that we use for communication purpose. In that also, this signal analysis is very important. What sort of a frequency you are giving to that particular crystal, and how that acoustic behavior of that crystal is changing. So this is another case. These two were actually the engineering related stuff, and I have so many files. I can just show the certain response. This I have a one file related to a bird's, I think, yeah, a little bird sound. So little bird singing in the trees also. So that also nature's response you can see here. Okay, so very small sound is there, but very intense sound was there. See, the frequency is so high. Okay, and here you see the histogram pattern for that particular sound file. There are different sound files. What I am doing with the LabVIEW now, I'm using this particular analysis for a disease or a illness detection, because during this pandemic we have seen um, that there is a need for a non-contact sort of analysis. Our temperature sensors, normal thermometers, are now being replaced with the laser thermometers, because contact types of sensors are I think will slowly will be replaced by non-contact sorts of sensors. So then we came with the concept that why don't we use the acoustic files, the sound files of various illness. Okay, so in this case, we took a database from an MIT, and they are doing that any sorts of disease actually first attacks your throat. Okay, that's because there are certain ways it enters with the nose, mouth. Okay, so first thing it makes its home is your throat, and you won't realize that you are suffering from a certain problem before you get a symptoms. The first symptoms is the your vocal cord frequency changes in presence of certain illness or certain disease. The first symptoms that you get, your vocal cord frequency. So there is a certain change in your the way you speak, the how you pronounce a particular word, that suddenly change from your healthy conditions. So then we are having a cancer, paralysis, polyp, cyst, COVID, and all those sorts of files we are playing, and we are actually measuring the power spectral density analysis, histogram analysis, and we are saying that just by taking a voice sample, whether we can actually detect a particular disease or not. So here I see, I think these files will not play because it's just A, E, I, O, U, some vowels they need to speak. A cancer sequence is there for the man. This cancer sequence we obtained from a Tata Memorial Hospital in Mumbai, Tata Cancer Hospital, and just A, I, U, all these vowels a person need to speak, and a diagnosis of cancer, at least a detection of a particular cancer can be done here. So some person speaks some A sound. So here this won't play. I think this is not in .wave format, but actually I can show the results here, analysis here. You see that this is a voice plot, amplitude versus voice plot for a healthy patient. You see here, this is the power spectral density. This is the histogram. This is a normal voice signal. Now, if I change it to a cancer one, the same file, you see there is a change. Now, see this amplitude versus time is also change. The power spectral density is so many side bands are there in this particular signal. Histogram is also slightly changed. So this is the way we can actually analyze any certain sorts of voice sample. So today's session, I actually use it to go for a certain mini project, because this tool has endless libraries. Even if I start today, maybe a year won't be sufficient to teach you this particular software. So many libraries, so many signal processing toolkits are there. It's used for robotics, used for machine learning, artificial intelligence, neural networking, all computer, IT, electronics, mechanical signals, acoustic signal, image processing. This tool is perfect. You can interface your Arduino, you can interface your Raspberry Pi, any sorts of oscilloscope, Tektronix. You can actually interface with your LabVIEW software. All sorts of drivers are available, and there are endless opportunities. So I thought better to go for a certain mini project that you understand that how to connect, how to give an input to a particular block, how to connect an output, what is a control, what is an indicator, and do some mini project. And that maybe in future, if you're interested in this particular part, then you can actually extend it to a very good project. So I think this is all I had for today. And if there are any questions, then I am open to all your queries.
Thank you, sir. Thank you for such a nice delivery and especially taking an example from mechanical, particularly from the vibration section. Thanks a lot. So, participants, any questions, please post in chat box or you can unmute yourselves.
Sir, I have one question actually. For getting the sound waves,
Yeah,
so we need to attach some sensors, right, on
yeah,
anything.
yeah. Huh.
So how to get that real-time data from the sensor to actually lab view?
Sir, that is also possible. Like for that, you need to interface your sound card of your PC. Okay, that I can actually show with a particular example also here in the lab view also. No need to actually just like your laptop has a PC as well as your laptop has also a sound card. So you can actually use that. It's a help file. There is a one program. Just I will show that. So the FTFT program. It's very popular. Just saw it. Yeah. You see that this particular program is there, and in this program, I can use a sound card and I can see this is a particular program. So basically, you have to give a device zero. So here you see there's a device zero. That's basically the sound card of your PC. Here also I have used a device zero, identity zero. Whether it's some your microphone or your speakers are there, and this device zero then configured with some certain things. And this sound, if I play here, so hello, 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 whatever I'm speaking is being plotted. So now this is a real time. Suppose I clap here, you can see some certain peaks are there, and you can see the spectrum analysis is also changing. So whatever sound you make, whatever I speak, and suppose there is some very sharp noise, I can actually see. So we can actually have a real time data analysis. This particular method we have used for a heart rate sensing. So basically, we get an acoustic response of the heart. That's a phonocardiogram, and this phonocardiogram is being plotted, and all response are being checked. So it's very much possible, sir. All sorts of hardware can be interfaced with this particular software.
Thank you, sir. Any other questions? So we don't have any.
Yeah,
Yes.
one question is there.
Yes.
Yeah.
Sir, what is VI the icon to get live data from Meet, from Google? Some kind of live data, any kind of live data, real data,
Here,
stock price or any other in VI.
sir, actually, basically, there is a NI community, National Instruments community. When you enroll for a LabVIEW software, whenever you download a LabVIEW software, they ask for a registration to National Instruments site. In that particular site, you go to NI community. In NI community, so many LabVIEW engineers all around the world are posting their problems and posting their data. So there's a complete data sets available in the National Instruments website, www.ni.com. www.nationalinstruments.com, so ni.com. You go there, you will find all sorts of a real-time set of data related to robotics, related to biomedical, related to communication, mechanical engineering. So there actually you can, or you can post your requirement that for a LabVIEW I want a dot wave data, and please, if you have some data, then they will automatically give you the drive link, and you can actually download it over there. So even if you post any problem, you are stuck to programming, within you can see the few hours you will get a response, and your problem, somebody will solve your coding problem, and somebody will send you the graphical code, and you can actually proceed further. So that's possible. And apart from that, so many websites are also there. You can just have to Google it that you want to have a particular data related to biomedical. So many healthcare sectors data are available. So it's possible. But that site is ni.com, nationalinstruments.com.
Okay, sir. Thank you, sir.
Yeah.
Thank you, sir, once again for giving us such a nice talk on simulation of LabVIEW software.
Yeah. Thank you, ma'am, for inviting me. And
Thank you, sir.
thanks for all the participants for your patience and time.